This is the final demo presentation regarding the intelligence-driven offloading for visual cloud computer systems, presented by Michelle Alfarhood, Suleiman Island, and Mauro Lemos. The goal of this project is the implementation of a proof of concept for an intelligence-driven computation offloading system based on a hyperprofile framework. It involves the scenario where mobile devices need to process visual data and give quick response to users. Due to the resource limitation of mobile devices, computational offloading may be required to expedite the response time. Our presentation includes the project motivation, testbed architecture, system architecture, and intelligence-driven offloading process steps. Our testbed architecture includes the modules of the system. As we can see here, the process starts by an access device who captures an image, detects its size, and sends a request to process this image to the system. In the system side, there is a module that takes the image size and combines this information with the network status provided by the monitor and also the neighbors features from a history database. It combines all of this information and trains an MLP multi-layer perceptron to generate a model that will predict some features that, combined with all the other information from the network, will create a hyperprofile model. This model will be stored in a OLAP cube. This data cube will process the data by calculating the distance from all the server nodes in relationship with the access devices. An MDX query will take the best node and provide the IP address to enable controller, which will define the path between the access device and the node in charge of process the image. In the system architecture side, we have the three main modules well defined. The first module will include two phases: the image capturing and size detection, with each done in the access device side, and the image processing, which will be completed in the server side. The access device captures the image, detects its size, and triggers the process by sending the image size and request to the controller. The image processing request is handled by the best server node that is determined by the other modules of the system. This module will make use of the TensorFlow Object Detection API and OpenCV framework to process the images. The second module will be in charge of predicting the parameters that will be favorable for particular node to identify the offloading server. The image size and the network status are the inputs for this module. This module will make use of a multi-layer perceptron MLP to process the data and provide the predicted results. The third module will be used to determine the best node that can process the data. It will use the parameters defined in the MLP module to build a hyperprofile module to include all offloading servers of the network, calculate the distance of each node in relationship with the access nodes, and identify the most favorable offloading node for any particular request. This module will make use of an OLAP data cube to represent the network model that includes all the nodes of the network. The following part will identify or will present all the steps of the process. In the following sections, we will demonstrate how the offloading process is triggered by the access device, how the multilayer perceptron trains the model, and how the access cube processes the hyperprofile data, and finally, how the visual data module processes the image to detect the face and identify the subject. The first part of the process starts by identifying the image size. A Python script takes the image and generates the size. The second part of the process includes the multilayer perceptron, who takes all the information provided by the network controller regarding the status of the current network, the size of the image provided by the previous step, and also historical data stored in a relational database, and combine all of these parameters and feed the multilayer perceptron to generate the predicted parameters. In this case, we are running the process to predict the transmission time and the processing time. We implemented a deep learning-based model, a multilayer perceptron MLP, in this project to train the intelligence-driven offloading system. The MLP has 3 hidden layers in a tower shape, meaning that each hidden layer has less units than the previous hidden layer. Each hidden layer has a rectified linear unit ReLU activation function. The ReLU is the most used activation function nowadays in deep learning due to its simplicity, fast training, and reduced to vanish gradient problem. The final output has the sigmoid function that generates values between 0 and 1. Therefore, normalizing the data labels is very important for training the model. Finally, the inputs of the MLP model, such as the data size and the image height, are concatenated in the feature vector layer. The feature vector layer is used to feed the model with inputs. We use 2 datasets to build 2 MLP models, as we are showing here. Processing time dataset and transmission time dataset. These 2 datasets are created by sending images from one source to another destination. First, the processing image dataset has 1600 instances and it contains 5 features: image size, image height, image width, and the CPU load, and the node type. Number of images that are used to create both datasets are 100 images. The data sizes of the images are ranged between 135 kilobytes and 3.4 megabytes. Also, the CPU load of processing time datasets has 4 values: 0, 25, 50, and 75. Moreover, 4 values are used as well for the node type that includes XO small, XO medium, and XO large, XOX large, that are the type of nodes that we can find in Genie. Moreover, 4 values are used as well for node type to include all these data types. On the other hand, the transmission time dataset has 700 instances and it contains 4 features: image data size, image height, image width, and transmission bandwidth. The image transmission bandwidth has 7 values. We use the k-fold cross-validation to evaluate our model with both datasets. Each dataset it splits into k-folds, such as the MLP model is trained within k1 folds and tests with the remaining fold. We repeated this process k times. In our case, k is equal to 20. Now we are seeing that the first part of the process is completed with the results indicated. The next step is related to the hyperprofile data-to-cube processing. In this case, the information provided by the MLP model is provided to the OLAP data load process. This process takes all this information and feed the data cube, creating the hyperprofile, outline, and data. Once everything is stored in the data cube, a calculation process identifies the distance between all the server nodes in relationship with the access devices. Once the calculation is completed, a MDX query retrieves the cube and generates the list of all the nodes that are the best option for each access device to offload the data processing. Now we are executing the script to load the data coming from the MLP module and then calculating the distance and generating the IP address. It was done for one access device. Now the script is executed for two access devices. Again, we reload the data into the cube, calculate the distance, and execute the query. It is done in less than a second, and we will get the two IP addresses to be sent back to the access device where the access device can offload the processing of the image. Now for three devices, again the process upload the data, calculate the distance, and generate the IP address list for all the access devices to offload the data. We are ready for the last part of the step, that is the image processing. Once the IP address is sent to the access device sends the image to the server node. Then the server node will process the image, what will contain three different steps: object detection, action determination, and facial recognition. This process is now executing the image processing. It will take the input image generated by the access device. Then the process will generate the structure, folder structure with the result. We are seeing this module being executed in real time. Now we are seeing the tree structure of the output, input and output. And now we are seeing the results. see the final results, we are navigating through the folder result. We are looking for the images generated by the process. We will see the results of the 3 steps we indicated before. We are seeing the object detection, action determination, and facial recognition. Also, we can see some statistics regarding the performance of the process. And it concludes our presentation. Thank you.